Alright, so welcome to Engineering 270, and we are going to continue talking about timers. I want to do a quick rehash on the timer 0 subsystem that we talked about in the previous video. A different way to think about what timer 0 is doing, and this works again for most of the timers in the PIC processor. So you're probably familiar with an hourglass, right? It's a piece of glass with sand sitting in a top half. When you flip it over, sand falls into the bottom, and so you have something like this. Right, you have sand up here, and it slowly falls down, and it drops into this lower region, and as this sand falls, this top region becomes empty. And when all the sand has left this top region, the time is up. So typically this is an egg timer. It's a 3-minute timer. And if all the sand is on the bottom, you flip it over, it takes 3 minutes for the sand to drain out. And the alarm goes off in some sense when this top part is empty. Okay, I want you to think about a similar idea, but sort of the opposite of that. Imagine a timing system built around a leaky roof. So here's the roof of your house, and there's water dripping down from it. And the water drips at a very constant rate. Okay, this is the instruction cycle rate, if you will. Water drops at a constant rate, and down here you have a bucket. And this bucket is filling up with water. And as the water continues to drip, the bucket gets more and more full. At some point, the bucket is completely filled with water. It can't hold any more. And the next drop of water that hits this, the bucket overflows. And when it overflows, water falls on you sleeping on your bed underneath, and it wakes you up. It interrupts your sleep. Okay? This is a pretty close analogy to how the timing subsystem works. So this bucket is slowly filling up. When it's completely full and then one more drop of water goes in, the alarm goes off, right? It spills water on you. Okay, now if we think about that, how long do you get to sleep when you're laying down on this bed waiting for water to overflow and interrupt your sleep? And there's a few factors. One is how often drops of water are falling into this bucket. If they're falling in very quickly, this is going to fill up quickly. It's going to be a very short nap. But if a drop of water is only coming in here very infrequently, if it's a long time between drops, it's going to take a long time for the bucket to fill. You're going to have a very long nap. So one way to control the length of this alarm is by controlling how quickly these drops of water fall into the bucket. And that's one thing we can do with the timer. Another thing we can do is change the size of the bucket. A small bucket will fill up quicker. That'll be a shorter nap. A large bucket will take more time to fill up. That's a longer nap. But there's a third thing we can do which gives us the most precise control, which is we can take our bucket, and instead of starting with a bucket that's completely empty, we can put a certain amount of water in it to begin with. So if we fill this bucket halfway with water, and then we put it over here and we take our nap, it's going to fill up in half the amount of time it would take an empty bucket to fill. And if we take our bucket and we originally fill it almost all the way with water, so that it can only hold a few drops before it's full, and we put that into our timing system, that's going to be a very short interval before the bucket overflows. So we have 3 ways to control this. The rate at which water is dropping into the bucket, the size of the bucket, whether it's a small bucket or a large bucket, and how much water we initially put into the bucket. Okay, so this bucket is what we call timer 0. It's 1 or 2 special function registers. The size of the bucket is this question: do we want timer 0 to be an 8-bit or a 16-bit register? If it's a 16-bit register, it can hold 65,536 drops of water. If it's an 8-bit register, it can only hold 256 drops of water. Okay? And the initial value that we put into this timer 0, that corresponds to how much water we put in this bucket initially. If we put a 0 into timer 0 to start, that's an empty bucket. If it's an 8-bit size bucket, which can go up to 256, it's going to take 256 drops of water before the timer overflows. If we fill the bucket up halfway, if we put it to a value of 128, it's only going to take another 128 drops of water before it's full. If we fill this almost all the way, if we put, say, 250 drops of water in this bucket, and it fills up at 256, it's only going to take 6 more drops of water before this is full. So loading timer 0 to an initial value of 250, assuming it's an 8-bit register, means that after 6 of these drops of water fall in, the bucket's going to be full, and the next drop it's going to overflow. Okay, give or take 1. I'm being off by 1 so that we don't get bogged down in details. Alright, so the size of the bucket is in this T0 configuration register saying, do we want this to be an 8-bit or a 16-bit timing operation? And so if you look at T0 con, which is the configuration register for timer 0, sorry, T0 con, right? There's a bit we can set to say whether it's an 8 or a 16-bit counter. Okay, that's the size of the bucket. The initial value we put in TMR 0, okay, that timer 0 register, which is, either 8 bits, timer 0 low, or 16 bits, low followed by high. That initial value is how full the bucket is to begin with. The dropping of the water normally occurs at your system clock divided by 4. Now if our system clock is 32K divided by 4, this is 8,000 drops per second. 8,000 instructions per second. This is our instruction clock. So we can think of this bucket as getting 8,000 drops of water in it per second. If it's set to overflow after 256 drops, right, it's going to overflow in much less than a second. Okay, there's one more thing we can do to control the speed of this. Remember, we can change the size, we can change how much water is in here initially, but we also said the rate at which these drops go into the bucket will change how long it takes the bucket to overflow. So here's what we can do. There's a system in the PIC processor which effectively it's your helpful monkey. Okay, this monkey hangs from the ceiling here. And here's what the monkey does. Normally it just washes the water dropping in, and every drop of water that comes out of this hole in the ceiling goes into the bucket. But if you ask this monkey nicely, here's what it will do for you. It will make sure that every other drop that comes out of the ceiling does not go into the bucket. The first drop of water that comes out, it will take and throw aside. And the second drop of water will go into the bucket. The third drop will get thrown aside. The fourth drop will go into the bucket. And now, even though we have 8,000 drops coming down per second, only 4,000 drops go into this bucket each second. Because this magic monkey, which we call Prescaler, is taking half the drops of water and discarding them. Okay, so that's the monkey called 1 to 2 Prescaler. There's another monkey which is called 1 to 4 Prescaler, and what that monkey does is it hangs out here, and it only lets every fourth drop of water go into the bucket. The first 3 drops that come along, it's going to take and throw aside, and then the fourth drop will fall into the bucket. And then drops 5, 6, and 7 get thrown aside, drop 8 into the bucket. So now, when 8,000 drops of water come out of this hole in the ceiling, only a quarter of them, only 2,000, will make it into this bucket. And you can see what's happening. The rate at which water is actually going into this bucket is getting lower and lower. The 1 to 4 Prescaler monkey is only letting 1/4 of the drops go in. And if we use the 1 to 8 Prescaler monkey, only 1 out of 8 drops go in. So after 8,000 drops have come out of this hole in the ceiling, only 1,000 drops have gone into your bucket. And it's going to take 8 times as long to fill up your bucket now. So this is the other way we can control this rate, the time that it takes for this bucket to overflow. Alright, and the rate at which this water is leaking out of the ceiling, ignoring the Prescaler monkey, that's the instruction clock. Okay, that's 8,000 ticks per second, 8,000 drops, 8,000 instructions per second. Alright, so when this bucket overflows, it does something funny. It doesn't just drop 1 drop of water on you, it completely turns upside down, so that now the entire contents of the bucket is dumped on you, which severely interrupts your sleep, right? It wakes you up, and then the bucket goes upright again, and it's empty, and it starts over. All right, so This is a little peculiar, right? We've got a magic monkey. We've got a bucket that miraculously tips over and empties out when it overflows. But take my word, this is what actually happens inside the PIC processor. There's a little bucket of water, and there's monkeys and all this kind of stuff. So that's an analogy to keep in mind if it helps. If it doesn't help, don't worry about it. But that captures the three main aspects of the timing system, which is being able to choose 8 or 16 bit, being able to put in an initial value into our timing register, and being able to control whether every single instruction tick increments the value in this register, or if every 4th, every 8th, 16th, or so on ticks causes an increment. Alright, so next video I want to talk about timing registers 1, 2, and 3, which will be very, very similar in basic behavior. Timer 2 will have a slight twist, but this should sound very much the same.